Hello, everyone. We now introduce Mr. Reynir Hilmisson, Business Development and Sales Engineer at Poseidon Systems, and he'll be sharing knowledge on advances in lubrication sensor technology. Welcome, Reynir.
Thank you. Thank you for the introduction and welcome all. First, I would like to say a big thank you to Sonia and Joss for facilitating this event. Big thank you for you all. So let's get going here. So when we're talking about condition monitoring and when we should apply it, reliability becomes a priority when the criticality of that machine increases for operations. Information about machine condition is essential for optimizing the maintenance and the reliability. And when we think of a target application, we could first think of these requirements. So what are the four groups of maintenance practices? We got run to failure, which is breakdown maintenance. This is for non-essential equipment for operations and still used in many applications. We have preventive maintenance, which is slightly more complex machinery, but still a simple fix where you periodically take the asset offline for inspecting or repairing. You got predictive maintenance, which predicts failures before they happen, so maintenance can occur at just the right time. And it uses data from machine sensors and smart technology. This can be offline measurements as well as online measurements, and it really depends on the machine criticality. Now, when we go to the fourth group, the last group, reliability-centered maintenance, RCM, or online monitoring systems. RCM is a highly involved process that seeks to analyze all the possible failure modes for each piece of equipment and customize a maintenance plan for each individual machine. And the ultimate goal of the RCM is to increase equipment availability and the reliability of that machine. So where are you and where do you need to be? And when you look at the graph on the right-hand side, when your cost of repair is higher than the cost of prevention, well, you're in the wrong group and you need to maybe consider where you should be. And to get to that optimum point, you need to understand the different failure modes and how they actually progress over time. So you can't manage what you don't measure. And to understand how these failure modes occur and how they progress over time, you need the right sensor. And this PF curve is all about representing the asset's behavior or condition before a catastrophic event. Monitoring machine performance in the proactive domain is often associated with highly critical machines. Now, these machines, they can also be very expensive and they require very sophisticated monitoring programs. But the PF interval is really the interval where you want to have the accurate details about the condition as it defines the failure lead time where the machine performance has reached its functional failure. Now, detecting the fault in its earliest stages and tracking that fault with accuracy will reduce costs and maintain a high reliability. So how often should you actually make a measurement and how often are there planned shutdowns for your machine? Planned shutdowns should not be later than the functional failure. So how do you make the best of your time? So go over here. You start looking for online sensors. You know, there are many different sensors out there which can do different things. And if you recall from the previous slide where we're looking at the proactive and the predictive domain, the health of the lubrication, amongst other things, in the predictive domain, proactive domain, and the health of the asset in the predictive domain, it can be monitored differently. And it must be selected carefully for each application when it comes to the correct sensor. Now, some of these sensors, there are a few direct measurements of lab data points. Some are correlating to lab data points continuously. And some of these sensors are providing new data points that you do not see in the lab data. So what is the value of online oil condition monitoring? Now, if you look at the graphs on the right-hand side, there is a theoretical example of offline oil analysis. So the time the sample is taken versus the time that you have your results, and most important, what happened in between. So being always on, This allows for earlier fault detection, which then in return enables a proactive maintenance strategy. So being online, it also tracks for rapid changes and accelerated fault developments, which is nearly impossible when you're only doing oil sampling. But this does, however, not replace lab analysis. But this allows the operator to optimize its sample rates and the sample time. So the different types of oil sensors found today, they're not measuring oil properties directly, but more measuring the overall state of the health over time, and is used as a trending tool. So when we think of an oil quality problem, there are several different parameters that can contribute. And as the overall health changes, so does the electrical properties of the oil. Now, these different contributions, whether or not this is oxidation, nitrations, contamination, water ingress, whatever it could be, this will affect the properties differently. And this is why we measure over a range of frequencies and not just a single frequency. And on the graph here on the right-hand side, you can see how the total base number correlates well with the sensor output trend. So by plotting lab results together with the online data, you can optimize alarm limits, which allows for a better detection of many oil quality problems. So this is measured at medium frequencies versus the ultra high frequencies, which is used in many sensors. And the importance of this, I would like to demonstrate here on the next slide. So here, there's a case study. We've used 3 different sensors. We're looking at the left-hand side first, where an oil quality sensor is used, measuring impedance over a range of different frequencies. The other sensor we used is a viscometer and a oil dielectric sensor, which measures at a single frequency. So a common diesel engine oil is tested and measured after being contaminated with successive amounts of fuel and engine coolant. And for the fuel added, which is represented with the red dotted lines on the graphs, only the medium frequencies and viscosity is responding to this. For the coolant, on the other hand, which is noted with the green dotted lines, only the medium frequencies response. So by having a sensor that measures over a range of frequencies, instead of only measuring one frequency, you'll get a better understanding of how different failure modes will affect your overall system. So in a case like this, when you see the step changes and you see the responses, a single sensor, or let's say the incorrect sensor, might have missed this contamination event. So to ensure the best performance of any machine, the lubrication has to be functional to achieve high efficiency and provide the protection needed against wear and tear. There are different approaches to achieve this understanding, and and how different particle sizes and the distribution of those particles can actually correlate to changes in condition. So you have your optical particle counting. This provides you insights into the oil cleanliness. You got the ICP AES elemental analysis. Again, this is used for detection of trace metals. But both these approaches, they do have limitations when it comes to particle sizes. And in some cases, flow rates might also be a limitation, and it can potentially be sensitive to air bubbles. But these 2 technologies can be used to establish knowledge about the lubrication itself, but not so much about the machine condition. And if you remember from the PF curve previously, lubrication is in the proactive domain, where the changes in the condition could be a root cause for a mechanical issue. But when we actually do have a mechanical issue, and when detecting and tracking those mechanical issues, we're now in the predictive domain, and different technologies are now more suitable for avoiding a potential catastrophic event. Now, our inductive coil sensing technology is designed to analyze wear debris generated from failures rather than the overall oil cleanliness. It detects larger particles, and it can differentiate between ferrous and a non-ferrous material, which allows you to determine where your potential failure mode is located in your machine. whether or not this is iron or steel, or whether or not this could be copper or some other non-ferrous material. It can help you give indication of where your fault is propagating. Now, here's a bearings ball case study from an industrial gearbox. The raw sensor output quantifies and qualifies ferrous and non-ferrous metallic debris into bins. This is seen on the bottom right-hand side of the slide here. So it classifies bin size below 100 microns to bin sizes above 700 microns. And if you look at the ferrous and the non-ferrous counts, which is being classified and quantified into these different bin sizes. So these bin sizes, they can be trended over time and giving insights over the development of the fault progression. But however, not all failure modes do have the same particle distribution. So instead of observing each bin size by itself, we've developed a live gauge measurement where the concentration levels is calculated from each count in each bin size. This is the red line on the graph, and this is a 24-hour concentration level, and it represents the amount of metal that has passed through the sensor. So we can also look at a 1-hour concentration level, and this gives a higher resolution and is usually used for more detailed analysis to understand the progression level of that failure mode. So these concentration levels as a function of time are better suited for alarm purposes, as each bin size alone might not give a good representation of the actual failure mode or the condition of it. So in addition to the concentration levels, we also calculate the total amount of mass that has passed through the sensor for a given time period. And as the daily concentration levels, which you can see in the red lines, well, as they start to get higher, the slope of the accumulated mass becomes steeper, the green line basically. So these two parameters, they give a better insights to the overall progression and the severity of the actual mechanical fault that we're looking at. And why is that? For some failure modes, we observe that particle distribution to remain relatively constant over the lifetime of the fault in certain failure modes. This is not applicable for all failure modes. And in this case, here the lifetime of the fault has been broken into 4 time zones, with time zone 1 being the early stage on the left hand and zone 4 being the late stage of the fault progression on the right hand side. So if we manipulate the data a little bit and look at it, so we go to the left hand side here on the particle count. We got a start and end date for each zone. You got a number of particles in each bin. And when you normalize the counts to the lowest bin of the first zone, the distribution of the particles remains fairly constant as the fault progresses. And by using empirical data like this, monitoring strategies can be implemented to target a specific set of failure modes and how to minimize and or even avoid operational conditions that can contribute to a wear generation and eventually a catastrophic event for that machine. So what we have seen in the industry and what let's call it long-held beliefs on wear generations, what we've seen that some of these beliefs are a little bit flawed. And the first belief is that the wear generation is an operation where particles are continuously generated over time. Our observations, on the other hand, suggest that wear particle generations are discrete events of burst metals that can be in hours, days, or even weeks apart. The second observation is that 99% of all damages, they occur in less than 1% of operational time. Now, the second belief here, the particle size counts increase exponentially with decrease in size all the way down to 0. So our observation is that wear particle counts, they do follow a skewed normal distribution, and with peak counting occurring somewhere between 20 and 30 microns. Third belief, wear generation starts as a small particle generation, and as the fault progresses, the percentage of larger particles generated increases. This is not what we observe. We observe wear particle size distribution, that is the ratio of large particles to small particles, they can remain relatively constant for a certain failure mode, and they can remain a constant as that fault progresses. And the only changes that we're seeing is the magnitude of the relative counts. The last belief, this is taken from maybe perhaps a different industry than you guys are used to, but wear generation amongst various towers in a wind farm are independent of each other. And this is not what we're seeing. Bearing spalls, like in the case study that we just looked at, those are driven by wind load conditions and are well time correlated events. And this suggests that both damage is not driven by oil condition, and that modified turbine operations during these wind events could actually result in a significant less damage and thereby life extension. So the real advances that we've achieved here have been by collecting a vast amount of wear debris data and analyzing these different failure modes and how they actually develop over time. So with knowledge gained from 20,000 operating hours, we have patented a method for analyzing wear debris data. And this was achieved by having the right hardware and the software, but most important, to have this massive amounts of data in our databases, allowing us to manipulate the data and manage the data in methods and ways that we've not done before. So this patent focuses on using an observed wear and operating conditions to predict future wear. And by manipulating the operations, we're actually able to reduce that future wear that might occur during those operational conditions. This has also established a correlation between load and wear generation. And then by applying de-rating strategies based on that analysis, we've been able to reduce the wear and extend the life on that machine. So before I finish off, I'd like to talk a little bit about our new technology here. This is our latest sensor. This is a 4-in-1 oil health sensor that enables end users to implement a low-cost reliability program. The target application for this sensor is designed for pumps, and it is mounted in the oil level sight glass and monitors 4 aspects of the condition. It monitors the level of the oil, the overall health of the oil, water contamination, and temperature. And in some applications that we've been approached by clients in oil refiners, for instance, they can sometimes have hundreds of pumps in operations. And by implementing a low-cost monitoring program for these pumps, the cost of maintenance can absolutely be reduced. The sensor output data is used as a trending tool, and it responds well to changes in the oil property, and it can measure the oil level with an accuracy of 2 millimeters. So when the level decreased, which is the blue line, and the temperature was increased, the gray line, the changes in the dielectric constant, which is the orange line, and the relative humidity, they follow very well and are correlated to changes these all 4 measurements. Now, I have limited data to share with you guys due to the fact that this is a very new technology. So we're going to have to suffice with the data that we're looking at here. But what is unique about this design is that you can add a vibration module to this sensor. And this takes the analytics to a complete different level, where you can monitor the health of the lubrication as well as the asset itself with one single sensor. The vibration module is a triaxial MEMS-based accelerometer, and it can generate time waveforms and fast Fourier transformation spectrums on demand. It also measures the magnetic flux, which gives you information about the running speed of the machine. And this enhances your analysis capabilities even further, because many failure modes within rotating machinery can be detected by observing changes in the running speed of that machine. So with all this data, what are we going to do with it? So modeling the operational behavior of a machine and how the condition changes over time can be done using the metadata and the data sources from these different technologies that are applicable for monitoring successfully a certain machine. But with wear debris data, oil condition data, vibration data, SCADA data, and even engineering models or digital twins, many damages can be avoided and even eliminated. So you have managing all the data in the cloud today, where you have access to tools that help you make sense of the data, has really changed the online conception. The Internet of Things has changed the game, in terms of storing the data, managing the data, compiling the data, and it's made it so much easier to realize many of these engineering models. But in the end of the day, it all starts by having an online sensor and getting that data and understanding the operational behavior and the different conditions associated with these different operational behaviors. It all starts with the online sensor. So, what is the right solution? And of course, it depends on the application. Is it a non-essential or is it a critical machine? What are the failure modes that you're expecting to see, and what are the parameters that you expect to monitor as changes which are connected to these failure modes? So the bottom line is that online condition monitoring, or OCM, it does not replace the need for lab analysis, but it does help reduce the number of samples, and it moves your lubrication program towards a more proactive approach. So with these words, I would like to say thank you and open for any questions you might have.
Thank you, Reynir, for the interesting and detailed presentation, and also sharing on the new technology that Poseidon has. Okay, I don't see any questions from the audience here, so I guess we can end the stream.
That's great. That means I was very clear about this.
Yep, I'm sure. Right.
Thank you all.
All right. Thank you.